Good morning, friends. It gives me immense pleasure to be here again for my course Engineering Thermodynamics. In this process, I am in module number 4. In this module, it is a power cycle. In power cycle, I have started with Otto cycle. As you know that this Otto cycle is a constant volume heat addition cycle. In this, the petrol and air which are sucked during the suction stroke is compressed, and after the compression, when a spark is there, that spark is given and the fuel burning is taking place, and this is taking place at constant volume. Then expansion is taking place. In expansion, we get the work done, and in the compression, we have to provide the work. So the net work done is work done produced by the expansion stroke minus work is absorbed by the piston during the compression stroke. Also, we know that from the first law of thermodynamics that the del Q is equal to del W. So we can find out the net work done by the differentiating the heat supplied minus heat rejected. Same way we have gone for the diesel engine, and in that the heat addition is taking place at constant pressure process and remaining processes are same, but heat rejection is there for Otto cycle, diesel cycle or the dual cycle. In all the three cycles, the heat rejection is taking place at constant volume process. This constant volume process, heat addition also and heat rejection is not really feasible because it is always in motion. You cannot make your piston to stop for instant of time. So, in the real sense, they are not the constant volume processes. Either the rejection or the heat addition in the Otto cycle or in the diesel cycle, the heat rejection is taking place at the constant volume. Also in dual cycle, we have mixed both Otto cycle and the diesel cycle. Some part is fuel burning is taking place at the constant volume in this way, and another part is taking place at a constant pressure process. So, the dual cycle is nearly real process except the heat rejection. In that also, heat rejection we are doing in the constant volume process, because if we make at a constant pressure process, the size of the cylinder is increased from 15 to 20%, which is not economical. The weight of this thing will increase, the stroke volume will increase, and the efficiency, it is not feasible to do the constant pressure heat rejection. By this drawback of these three engines, Brayton has thought to develop the cycle, and he has developed the cycle in which it is like a diesel cycle except the heat rejection is also taking place at a constant pressure process. And initially he has made the piston engine, but it was very big, very heavy, and could not be a very good success in this process. However, after some decades, the Brayton has this, in the Brayton cycle, the gas turbines were developed, and they are the continuous process, not a piston engine. They are the rotary engines. So in that, we have the compressor, we have the combustion chamber, we have the turbine, and they all are the rotating. So this way, we can at a constant pressure, we can burn the fuel, and also constant pressure, we can exit the gases which are burned after using the turbine. So this gas turbine engine was developed on the Brayton cycle. I have given some brief of this thing, and today I am taking the second part of the Brayton cycle, and in this we will be solving some numerical, mostly 2 numericals we will be able to solve in today's topic. So numerical 1 is Brayton cycle work done and efficiency. Numerical 2 is also Brayton's cycle, work done and the efficiency. So here we have the first problem. I will read out, then we will try to solve this problem. Consider an ideal air standard Brayton cycle in which air is compressed to 100 kilopascal, 20 degrees centigrade, with pressure ratio across the compressor is 12:1. The maximum temperature of the cycle is 1100 degrees centigrade and air flow rate is 10 kg per second. Assume constant specific heat for the air. Determine the compressor work, the turbine work, and the thermal efficiency of the cycle. So here it is a standard Brayton cycle. First thing is given, this is a standard Brayton cycle. So we know the Brayton cycle, so we have to draw the Brayton cycle. So 1 and 2 is a compression, 2 to 3 is a constant pressure heat addition, 3 to 4 is a, so 1, 2, 3 and 4, and here it is constant pressure heat rejection. This is the QR, this is the Q in, this is the compression, this is the expansion. Expansion, S is equal to constant, here S is equal to constant, this is called the compression. So these are the things which are given here. Compression is 12:1 and this we will be solving in the, so first we have to draw this PV and the TS diagram. So this is the 1 to 2, it is a compression. This is S is equal to constant. 2 to 3 is a heat addition, QA. Then we have 3 to 4 is expansion. Entropy is a constant. Here is P is a constant. And here also P is a constant. Isobaric process. So all the process. So here 1 to 2 compression, adiabatic, reversible adiabatic. 2 to 3 is heat addition at constant pressure, isobaric. 3 to 4 is expansion at adiabatic, reversible adiabatic or isentropic, and 4 to 1 is heat rejection at constant pressure. If you see the TS diagram, in TS diagram also we can see that it is a adiabatic or isentropic process. So 1 to 2 is a compression. I am writing here compression. In this pressure is increased from 1 to 2, P1 to P2 here. P1 to P2, it is a compression ratio. P2 by P1 is given. It is a 12 and this is a 1. Compression ratio is given. Now you have increased from 1 to 2. Now you have added the heat. You have burned the fuel here starting at the 2 and it is reaching at the 3. So 2 to 3 is a adiabatic, this isobaric compression. So here 2 to 3 it is a constant pressure. I am writing P is equal to constant. From 3 to 4 it is S is equal to constant and it is called expansion, and here is a heat rejection. I am writing heat, it is out and heat is in. So this I have given a small brief on your problem, and here what are the things are given? P1 and the T1. This point is given. Here the P1 is 100 kilopascal. So this is the 100 kPa. And this T1 is how much? It is a 20 plus 273. So 293 Kelvin. It is given. And RP is 12:1. So RP is equal to 12. T maximum is a T3. So what is the T maximum? This is the T3. T3 is given as a 1100 degrees centigrade. So this is the maximum temperature at which after burning of the fuel, the turbine is getting the temperature of 1100 degrees centigrade and the mass rate is given 10 kg per second. So now we have to find out the step by step. So first we will do the compressor work. So we know the compressor work is equal to H2 minus H1. And we can write for air, it is equal to Cp T2 minus T1. But we don't know the T2. But we know the P2 by P1 is equal to 12. So T2 by T1 is equal to P2 by P1, gamma minus 1 by gamma. So Rp, gamma minus 1 by gamma. Rp is given 12 here. This you can see. Rp 1.4 minus 1 by 1.4. So here temperature is 1100 degrees centigrade plus 273, 12, 0.4. So you will get here this T2 you will get. Please calculate it. Please calculate this value. Okay, it is not, I have not shown here. So now we can get, we have to get now T3. T3 is given. So we need to find out T4. So we know that for the isentropic process, T3 by T4 is equal to P3 by P4 and P3 is equal to P2 as a constant pressure process. P4 is equal to P1. We can write as a P2 by P1 here and P2 by P1 is equal to 12, 1.4 minus 1 by 1.4. So you will get that T4 is equal to T3 divided by Rp, gamma minus 1 by gamma. So here 1373 divided by this, you will get some value. Please calculate. Please calculate from yourself. You will get some value in Kelvin. Okay. Now turbine work. What is the turbine work? We can see that H3 minus H4. Cp T3 minus T4. So we know this and we have got this here. So this value Cp is equal to 1.005, 1373 minus here T4, which we have got from here. You this put the value, you will get some value here. You will get here 701.3. Okay. So now rate of work done, mass rate is given 10 kg per second. So here 10 into Wt. So 703 into 10, you will get 7013 kilowatt. So this is the work done by the turbine is 7013 kilowatt. Now you can find out the efficiency is equal to eta is equal to 1 minus work net divided by QH. So QH is equal to Cp T3 minus T2 and work net is equal to Wt minus Wc. We have got all these items. You just put the value. You will get 0.509 and you multiply it by 100. You will get in percentage because we have to get the efficiency in percentage. So we will get the efficiency is 50.9%. It means the Brayton cycle is used to model gas turbine cycle engine used for aircraft, ships, power plant. And by this way, you can calculate the how much work is required for the compressor, how much we can get the work, how much maximum compression ratio, which we have already derived in the previous lecture, that it is related with under root T3 by T1. So these all equations, you can use it. You can design your all the parameters, your engines, your turbines as per given equations. Hope you have liked this, understood this problem. Very simple problem. And now I will go for my next problem. So here the pressure ratio and the maximum temperature of a Brayton cycle are 7 and 1000 Kelvin. Air enters the compressor at 1 bar and 303 Kelvin for 2 kg per second of airflow. Determine the work input in a compressor, turbine work output and the thermal efficiency of this cycle. So here it is Brayton cycle. That you have to see that which cycle first you have to see. Then you have to see which media, air is used or anything is used, that you have to. And maximum temperature is 1000 Kelvin. So here T3 is equal to 1000 Kelvin. The pressure ratio P2 by P1 is equal to 7. P1 is equal to 1 bar and T1 is equal to 303 Kelvin. So these parameters are given and by these parameters we can find out very well all the things. So here Rp is equal to 7, T3 is equal to Tmax is equal to 1000 Kelvin, T1 is equal to 1 bar, T1 is equal to 303. So here 303, this is given as a 1000 Kelvin. This is also Kelvin. P1 is 1 bar here. A mass is given. So we know that for the compression process 1 and 2, for a isentropic process, this is the S is equal to constant. Here also S is equal to constant. S3 is equal to S4, and here S1 is equal to S2. So it is a constant entropy process. So we have to use for 1, 2, T2 by T1 is equal to Rp, gamma minus 1 by gamma. So T2 is equal to T1 is equal to 303. Rp is given 7. 1.4 minus 1 by 1.4. So you will get the T2 is equal to 528.6 Kelvin. So we have find out here. So we got here T2 is equal to 528.6 Kelvin. So now we know this, we have to find out now T4. So if you know all the temperatures, we can get all the things. So we need to find all state points. So now we will go for the process 3, 4. So 1 to 2, 2 to 3, 3, 4 is again, it is a isentropic expansion. So we can use that T3 by T4 is equal to Rp, gamma minus 1 by gamma. So T4 is equal to T3, Rp, gamma minus 1 by gamma, 1000 divided by 7. So you will get here T4 is equal to 1473 Kelvin. 1573 Kelvin. There is some problem here. Okay, so to find the compressor work done, Cp T2 minus T1. So we got this. Work done is equal to T3 minus T2. T3 minus T2. It is not T3 minus T2. It is T3 minus T4. So here it is 573. Not, sorry, this is wrong. Okay, that's why I am telling that here 1000 minus 573.19 Kelvin. So here you will get the work produced by the turbine is m dot Cp T3 minus T4. M dot is equal to 2, 1.005, 1000 minus 573.19. You will get the turbine work done is equal to 857.88 kilowatt. So this is the answer. Now, if you want to find the thermal efficiency of this cycle, it is a net work done divided by Qin, Wt minus Wc by Qin. So Wt we know, Wc we know, Qin is equal to mCp T3 minus T2. So 857.88 minus T2 is equal to 453.45. 2 into 1.003, 1000 minus 528.6. So we will get this thing as a 0.427 or 42.7%. It means the efficiency of this cycle as an ideal cycle, we are getting only 42%. But in the real scene, we will not get everything ideal. So many things, dynamic frictions, entropy will never remain constant. So the actual engine for this type of scenario may be 30%, 32%, not more than that. Means if you spend 1 liter of petrol or any fuel, you will get only 42% of the real what the energy the petrol is exhibiting. Suppose 100 joule, actually you are getting 42.7 joule. But in the real scene, you may get 30, 32, 33, 34, 35%. So that much, 60 to 65% of your petrol is going waste, which is in the atmosphere. That is why a lot of pollution is taking place, and the greenhouse effect will be there, and the ozone layer will be depleted. That is why slowly the system is converting to the green technology, where we can use the green things. Thank you. I think next class I will be taking for the introduction to Bell Coleman cycle, Bell Coleman cycle diagram, construction of Bell Coleman, PV and the TS diagram, working of a Bell Coleman cycle, process in the Bell Coleman cycle, aircraft refrigeration system, COP derivation of aircraft refrigeration system. So as of now, we have done the heat producing devices. In heat producing devices, we have seen the Otto cycle, diesel cycle, dual cycle, and the Brayton cycle. These first three cycle, Otto cycle, diesel, and the dual are the piston engine, and the last one, it's a Brayton cycle, is a rotary engine or the gas turbine engine. And we have seen that they all are the work producing device. Next, I am going to talk about Bell Coleman cycle, which is work absorbing and heat extraction devices like refrigeration, air conditioning, or heat pump are working in those principles. This I am going to discuss in my next class. Hope in that I will be covering the real aircraft refrigeration system, and you will see that how in aircraft we use only air as a refrigerant. We don't use any HCl gases. We don't use any green or any polluting gases. Only the real atmospheric air we are using. So very clean air conditioner of the systems are used. So these are the references. PK Nog, Engineering Thermodynamics, Tata McGraw-Hill's, Yunus Senegal, Michael A. Bors, Thermodynamics and Engineering Approach, Tata McGraw-Hill's. Any questions, you are always welcome to ask. My email is ydwivedi@gmail.com. Okay, so you can like, if you like this video, please like and subscribe it. Thank you very much. You can also give the comment. Till then, goodbye. See you. Thank you very much for joining.
Like, share and subscribe. Hit the bell icon for more updates.